Good afternoon, ladies and gentlemen. Thank you for joining us for this webinar on the impact of the physiological responses to extreme environments on cognitive function. Before we get going, just a couple of introductory remarks, which are basically housekeeping. Our speakers will each deliver 20-minute presentations, and then we'll have 15 minutes for a Q&A. I hope you'll engage with that. Please submit any questions through the Q&A button at the bottom of your screen. Questions will be directed to the speakers during the Q&A portion of the webinar, but please do submit questions at any time, as we'll be monitoring these and presenting them to the speakers at the end. You have the option to submit questions anonymously if you'd like to, but if not, please include your institution at the beginning of your question so we can announce this with your name. We might not have time for all the questions, but we'll try to get through as many as we can. You can also upvote questions to type your own answers or comments to the other attendees' questions, so you can do that as well. The webinar is being recorded and will be available to re-watch for those of you who are in drastically different time zones. There's a little bit missing out of the title, and it's that last bit there, a little considered loop. And that's really part of what we're going to explain to you today. I'm Mike Tipton. I'm co-chairing this webinar with Prof. Carolyn and Greig from Birmingham, and Caitlin Oates from the PhysSoc helping out. And our speakers are Joe Costello and Matt Wilkes. The branch of biology that deals with the normal function of living organisms and their parts is physiology. And interestingly, when you Google physiology, you get lots of diagrams like this. And I think there's an essential organ missing from these kind of diagrams. And of course, it's the brain. And it's often the first of the major organs to be impacted by extreme environments. We know that from cold. You see changes in personality, you see amnesia. We know it in heat, we know it at altitude. But we've always, as physiologists, been relatively reticent about getting involved in looking at the cognitive function. So the loop we're going to discuss this afternoon is presented here. We have an environmental stressor that produces a physiological response. That environmental stressor may be cold, heat, altitude, pressure. And we have a pretty good mechanistic understanding, if you look through the literature, of the responses that that kind of exposure or stimulus provokes. A good understanding of the physiological components of that. But part of those physiological responses are changes in brain function. And we are much less well versed with the mechanistic components of that particular change in function. And the alterations that change in brain physiology has on cognitive functions, things like decision making. When it comes to the decision making cognitive aspects, for example, we understand in a descriptive way what happens and the impact on the change in behavior, but we have a much less precise understanding of the mechanistic alterations. And as physiologists, we tend to stop at the second circle here. We tend to stop at an understanding of what happens to the physiology. And yet, in many real life situations, what happens is people continue around this loop. They have alterations in their brain physiology, which changes the way they behave, which changes what they do, which then often augments the stressor. And they continue going around this loop until they end up in serious problems. We also know from research that this change in behavior can be produced by things like variations in the amount of competition there is in an environment. We also know it can be altered by bullying, drugs, and there are differences in personality. So what we want to explore today, as I say, is this loop around which we go in the real world, but at which we don't tend to go around when we do our research in extreme environmental physiology. And partly that's because we are a little bit pigeonholed in terms of our expertise, and to continue around that loop means we may have to collaborate with those in psychology or neurophysiology. That I think is an important thing to do in order to get a full understanding of what's happening in the real world. So the aims of the webinar is to highlight for physiologists the strategic and scientific importance of considering cognitive physiology and associated with different interventions, to consider the best methods for assessing cognitive function in different conditions, and to describe some original research work examining the impact of hypoxia on cognitive function and consequent physiological status. And there's the program. I've done now the introduction, and I'll move on to introducing presentation one. We'll then have a second presentation, a Q&A, as I've said, and then I'll finish with some closing remarks. So our first presenter is Dr. Joe Costello. He's a senior lecturer in exercise physiology in the Extreme Environments Laboratory at the School of Sport, Health and Exercise Science at the University of Portsmouth. Prior to joining Portsmouth, Joe completed a PhD at the University of Limerick in Ireland and 3 years postdoctoral research at Queensland University of Technology in Australia. He is the Extreme Environments Thematic Research Lead at our university and chair of the ethics committee within the group. His research degrees coordinated within the school in addition to those other roles. He has published 76 full peer-reviewed articles. His primary research interests are directed towards exploring the mechanisms responsible for a decrement in performance, both physical and cognitive, following exposure to extreme environments. Thank you very much, and over to you, Joe.
Thanks, Mike, for that introduction. I'm just going to get this presentation up in the background. And thanks, everybody, for joining this webinar here today. So what I'm going to talk to is give a bit of an overview of some of the original research we've done in this space. And hopefully, as Mike alluded to, this will set up my co-presenter, Dr. Wilkes, later to talk more about the applied work he's doing in this space. So I suppose the background to this research that I'm going to talk to you today about originated from a review we did a couple of years ago and published in Neuroscience and Biobehaviour Reviews. It was led by our colleague, Professor Terry McMorris, and it was on the acute effects of hypoxia on cognitive function. So we sought to systematically review the entire literature based to see what was out there and what was known about the effects of hypoxia on cognitive performance. So what we found actually surprised us a little bit. We found only 22 studies comprising of less than 450 participants. So that was the entirety of the evidence base in this space. Hypoxia did indeed appear to impair cognitive performance, and these results were similar regardless of whether the hypoxic dose was hypobaric or normobaric in nature. And the key predictor of cognitive performance was PaO2. However, the key findings from this systematic literature review and meta-analysis were as follows. As I mentioned previously, it was a very, very limited evidence base. There was significant ambiguity surrounding the type of task or cognitive tasks that were impacted. And many of the studies lacked a normoxic or control group. There were often single experimental design, hypoxic dose, and a pre-post response. The studies in general were very descriptive in nature. So the majority of the studies, in fact, nearly all of the studies, limited any mechanistic insight in an attempt to explain I suppose, the cause of this cognitive decline when exposed to an hypoxic environment. So what we sought to do was to examine cognitive performance during exposure of a range of mild to moderate normobaric hypoxic exposures. And we've published this literature, this study, late last year in Experimental Physiology. And this study was led by one of my PhD students, Tom Williams. So we had two primary hypotheses. The first one was that performance of the more complex central executive tasks would be more susceptible to hypoxia, and that's compared to the more simple tasks, and I'll talk more about that in a second. Our second hypothesis was that cognitive performance would be correlated with changes in SpO2, cerebral oxygenation, and plasma adrenaline, noradrenaline, cortisol, and copeptin. So I'll come back to those hypotheses at the end to see what we actually found and what we reported. So we recruited a convenient sample of 12 healthy males. Their demographics are displayed here. We did a thorough health screening involving a 12-lead ECG, a full blood count, and a health history screening as well. In terms of the methods, we had a single blind. So single blind here, I mean, it was participant blinded, and that was key. We found a lot of the research in this space, it wasn't participant blinded. So the participants knew exactly what environment they were in or being exposed to, and the conditions were randomized in a controlled design. We did a health screening, as I talked about, and a thorough familiarization. So this was a familiarization of all the cognitive battery that we were going to assess and use, and also all the physiological variables that we were going to record. And then there was 4 experimental trials, and I'll talk to them in a second. It was 60 minutes of exposure, and it was an environmental chamber in our lab set to 24 degrees Celsius and 50% relative humidity, and the participants remained in a semi-reclined, rested position throughout. We had a 48-hour washout period between each trial. So the trials consisted of breathing an FiO2 of 0.2093, 0.17, 0.145, or 0.12. And their approximated equivalent altitudes are displayed there on the right-hand side, up to approximately an altitude of 4,300 meters. I'm just going to run through some of the tests and the actual cognitive tasks that we did now. And as you can see, or as you will see, they increase in complexity and difficulty. So the first one we did was a simple reaction time and a choice reaction time task. So these tasks are considered non-central executive, so more simplistic, and they typically measure general alertness and motor speed. On the left-hand side, it's the simple reaction time. So a stimulus appears on the screen, the participants had to press a key. And then the second trial was choice reaction time, where there was a number of potential stimuli that were presented, and the participants had to respond quickly and accurately. So there was 20 trials in both the simple and the choice reaction time task. And I should say all of these tasks were delivered on a personal computer, on a laptop. The next task we did was the Ericsson flanker, or modified Ericsson flanker test, which is a central executive function task, and it typically measures inhibition and selective attention. So there's 2 forms, congruent or an incongruent, that the participants were given as a display on the screen. And the top one, the task is to identify whether the arrow in the center is going left or right. And the top one, you've got the congruent arrows either side, and in the bottom one, it's the incongruent one, where it's on the right-hand side, but you've got the distractors either side pointing the opposite direction. And this was presented over 30 different trials. The final task we examined was the 3-back. So this is a modified version of the in-back task. So this is a central executive function task, and it assesses working memory. As you can see here in the screen, the participants are delivered a series of letters. So it's, in this example, G was presented 3 times previously. So the participants had to identify that G was the 3-back in this instance, and there was 30 trials delivered. Throughout the 60-minute exposure, we measured a battery of physiological variables, including cerebral oxygenation, SpO2, breath-by-breath respiratory data. We took a blood sample before and 60 minutes after the exposure. We also measured skin blood flow close to the site of the cerebral oxygenation, the NIRS device, and heart rate. In addition, we recorded perceptual measures of acute mountain sickness, mood disturbance via the POM measurement, and also breathing difficulty. Suppose in the interests of time and for today's webinar, I'm going to mainly focus on the NIRS data. So that's the cerebral oxygenation, the SpO2 data, and also the biochemistry data. So as predicted and by design, what we wanted to do was set up a progressive reduction in both SpO2 and cerebral oxygenation. So on the left-hand side here, what we have is the SpO2. On the vertical axis is the peripheral oxygen saturation, and on the x-axis is the pre-post exposure. What you can see is we got a nice decrement or decrease in SpO2 as the severity of the hypoxic dose increased. And at the most severe hypoxic dose, an FiO2 of 0.12, you can see on average the SpO2 is approximately 80%. On the right hand side, this is the tissue saturation index, and I'll come back to this again. Again, there was a significant reduction to about 7% decrease from baseline in the FiO2 0.12 condition. So this is the plasma biomarkers. I have the change in adrenaline, noradrenaline, cortisol, and copeptin. So what I mean by change there is from baseline to after the 60 minutes of exposure. We didn't find any significant increase in any of these biomarkers, and this, in hindsight or on reflection, was probably not surprising because of the short duration of the hypoxic stimulus. So it was only 60 minutes. And the participants remained rested throughout, so the metabolic rate was quite low. And finally, it was mild to moderate hypoxic stress, so it wasn't a real severe low FiO2. None of the aforementioned cognitive tests were impacted or impaired except the IMBAC trial, which was considered the most complex of what we delivered. So what this figure shows on the y-axis is the change in the accuracy of the task. And on the x-axis, I have the different environments. And you can see here in the 14.5% O2 and the 12% O2, there was a significant reduction in the accuracy of this IMBAC, the 3-back task. I suppose the most interesting thing, or the thing that we wanted to really take a step further and go beyond being descriptive, is try to actually figure out what was linked to or potentially causing some of these cognitive decrements. So over the next couple of slides, what I'm going to show is the change in the SpO2, and this is on the x-axis, and also the change in accuracy, which is on the y-axis. And all individuals are represented here across the 4 different environments. So the first thing you will see is a huge spread in the data. There's a significant inter-individual variability when exposed to the same 4 environments between individuals. And what we found was a significant correlation between the change in SpO2 before and after the 60 minutes and the change in accuracy of the IMBAC task. And this was also represented in reaction time, so the speed of the response, not just the correctness of the response. And as you'd expect, as SpO2 decreased in some individuals, it was down to about negative 25% from the baseline, reaction time increased, so there was a negative relationship. And for the first time, we were able to also demonstrate that tissue saturation index, that's the TSI, which is the change in the oxyhemoglobin divided by the change in total hemoglobin expressed as a percentage. So similar on the right hand side here again, I have got the accuracy, the change in accuracy of the IMBAC, and on the y-axis is the change in the TSI, with one individual there down to about a 10% reduction from baseline. We found a significant correlation there. Similar, we found a negative correlation between the reaction time. Again, as the TSI decreased, reaction time increased. So in terms of the findings as a whole, what we reported was that the 3-back accuracy decreased in the FiO2 of 0.145 and the 0.12 trials. The 3-back performance was correlated with the SpO2 and the tissue saturation index, but not plasma catecholamines and stress hormones, as previously been alluded to or speculated in the literature. And I suppose just to reinforce the previous point, the majority of the inter-individual variation or variance in cognitive performance following exposure to hypoxia still remains unaccounted for. So thank you very much. I'm going to pass you over to Dr. Wilkes now, and he'll take it on from here. Actually, Mike is going to take over, I think, and introduce him first.
Yeah, thank you very much, Joe. It was fascinating. And then really, whilst Matt is loading up his slides, I'll introduce him to you. Dr. Matt Wilkes is a doctor with a background in anaesthesia. He's a final year PhD student with us at the Extreme Environments Laboratory. His project focuses on the effects of the physical and technological environment on paragliding pilot safety. The work has led to practical changes in the pilot training and equipment and has been awarded the Aerospace Medical Association International Scholarship, as well as the Royal Aeronautical Society GP Ollie Research Award in Aviation Medicine. Matt has worked as a volunteer physician at high altitude clinics in the Khumbu and Andes, as a paraglider pilot and guide. He has flown above 5,000 meters on a number of occasions in the European Alps and in the Himalayas. Over to you, Matt.
Thank you very much, Mike, for the introduction, and thank you very much for having me to speak today. As Mike said, I study paragliders because somebody absolutely has to, and I'm particularly concerned about their safety, partly because I fly, but also because I've lost friends flying, and it underlines to me when I do this work really why I want to make sure it's done as well as possible. And what I'm going to talk about today is really some of the challenges inherent in doing this work. When we look at our paradigm that we set out at the beginning, we have these environmental stresses, we have the physiological responses. Apologies. Sorry. We have the physiological responses. But when you start to bring in behaviour, which is what really matters when we come down to safety, things become more difficult. And in fact, you often end up with a gulf. You have this lab work of the kind that Joe and Tom are doing, this really well-controlled, precise way of looking at specific questions. And then you have the messiness that is the complex behavior of humans doing a complex activity like flying paragliders in an ever-changing environment. And linking the two often seems like trying to bridge an impossible gap. So what I'm going to talk about over the next 15 minutes or so is some of the ways that we've approached this, both the ways that we have done and also perhaps the ways that I wish I had done. So let's start with a real life example. This is a video from Nicolas Plin. And he's flying over Mont Blanc in July 2019. In July 2019, we had a really high cloud base. And for one of a handful of times in the last decade, it was possible to fly over the summit of Mont Blanc. You'll see that there's already a large crowd gathered on top, and you can also see a bunch of pilots kind of scattered below. Now, I know I'm speaking to an audience of paragliding aficionados, but for those who've not done a lot of flying, you can see he's actually coming in rather fast. So that was his landing. So far, so good. Let's look at what happens when he tries to take off again. As he prepares his takeoff run, again, he's running quickly to try and airspeed. And those who are looking closely will have seen that as he takes off, he passes over these two gentlemen here. Now, at the bottom of the screen is a French mountain guide, properly equipped with crampons and an ice axe. Below him is a German paraglider pilot wearing trainers, and the mountain guide is towing the paraglider pilot's paraglider back up the hill. So how did these gentlemen find themselves in this situation? Well, the first question to me is, how did they get up there? And we could hypothesize that flying a paraglider doesn't take much physical effort. We could say that this allows you to control a paraglider despite a 4,000 meter gain in altitude unacclimatized. But you might also speculate that the paraglider had very little reserve. You could hypothesize that taking off requires more effort than flying. So actually taking off at altitude is going to be particularly hard. It's going to be particularly challenging. You have to run faster to get enough airflow over the wing, and you may have very little margin when you do so. And then you can also speculate that landing high and then taking off again can be a dangerous thing to do. And unfortunately, in the case of Mont Blanc last year, this proved to be true. There was one death, and actually when you look at all the footage over the course of the day, it's surprising it was just one. There were people strewn all over the mountain. They were being rescued by mountain guides. It was a scary thing to see. So my question to somebody who's interested in safety is, why did they behave this way? Now, if you're interested in the outdoors, particularly if you do a lot of skiing or winter mountaineering, you'd be very aware of avalanches. People have done a lot of work into behavior in avalanches. Why do people who should know better still get avalanched? And they come up with lots of human factors explanations, everything from following an expert to summit fever. That may apply in this case. But the question we're trying to address here is what part does physiology play in this behavior? So the first part, that first hypothesis that flying a paraglider might not require a lot of effort, that's very testable. And actually, we went on to test it. We did in-flight CPET testing in a small group of pilots flying at 3,000 meters. If you look at the VO2 figure, you can see that their baseline values are low, as you'd expect, and their in-flight values, the values for thermals and gliding, aren't much higher. In other words, flying a paraglider does not consume that much more oxygen than sitting in a chair. Effectively, you're sitting in a chair in the sky. However, when you come to take off, while it still doesn't require a lot, that requires quite a lot more. Some explanation.
So the first part of that hypothesis that flying paraglider.
So let's go back to here. So we've said these people have put themselves in a position of environmental stress. We've perhaps taken a look at how they might respond physiologically. But now, how do we link that to cognition and that to behavior? And this is the real methodological challenge. You come back to this gulf between the control of the lab, the work that Joe's doing, and the ecological validity of a complex activity. And so the way I started off to do this was I thought, well, I'm interested in the effect of the environment. I want to know how paragliders respond. Let's give these people a paragliding task. The problem that you then have is if you're comparing between subjects, it's very hard to tell those who are impaired and aren't good at the task because of the environmental stressor versus those who are actually just less good at the task in general. Are you not doing well because you're not a good paraglider pilot, or are you not doing well because you're hypoxic? So you then think, well, let's compare within subjects. But then the issue then becomes one of repeatability. This is something called the human factors and classifications system, Wiegmann and Chappell. It's a way of looking at all the factors that play a part in pilot error. So let's say in our task, our ecologically valid paragliding task, we were looking at skill-based errors, the simplest thing. Do they control the wing how they should? This shows all the different factors that feed in to that skill-based error, of which adverse physiological states is just one. And keeping these consistent, even for within subject designs, is a difficult thing to do. The other thing is that if you're like, okay, well, I shall get rid of the paragliding element of the task, let's use a validated cognitive test of the kind that Joe did to level the playing field, is if you then try and do that in the environment, if you say, let's do a validated cognitive test while someone is flying, you then have a problem of divided attention. Are they not doing well on the test because they're not paying attention to the test? Or are they doing very well on the test, but they're not paying attention to flying, and then they might crash? As a result, we and a lot of other people in this situation arrive at simulation as a solution. And that's what we tried to do. We tried to pick the environmental stresses that we thought were key. So hypoxia, cold, a headwind, in some of our other studies, G-forces. We tried to simulate those and then use validated cognitive tests. Now, when we did that study, we found that flying, we were concerned more with lower altitudes than Mont Blanc altitudes at which there was a little bit more uncertainty. And we found an enormous amount of individual variability, which made it hard to draw definitive conclusions, certainly conclusions that we could use to inform behavior or safety research. So the problems we found are the problems common to simulation and these kind of studies. Sample sizes were small. There was high individual variability. Quantifying degrees of our stressor is not always easy. As Joe showed, yes, if you diminish normobaric hypoxia, you will get a decrement in SATs. You will also get a decrement in tissue oxygenation that follows the same trend, but actually in absolute terms is not quite the same. So if we're now thinking about domains of cognition, about specific areas of the brain, we need to think about regional, not just whole body hypoxia. Joe mentioned practice effects. Now, these can be overcome through trial design, but like simulation itself, it's laborious, and as a result, your sample size is limited. But the biggest problem with these complex or dangerous activities in simulation is in simulation there aren't consequences. If you make a decision in paragliding, it can cost you your life. If you make a decision in a simulation, you might lose the game. And that, to my mind, is a fundamental confounder when you're looking at behavior. And then finally, when you're trying to make that link between cognition and behavior, the significance of the cognitive test results is not always clear. If I show, as Tom and Joe did so elegantly, that there's a decrement in your NBAC task, what does that mean about the decision you're going to make when it comes to landing on Mont Blanc? How do we link those two things? So if you have a cognitive test result, even if you account for all the others, those other limitations and problems, will it predict behavior, and will it do so in a way that is generalizable, not just in your population? So I would argue that at this point, as Mike said at the beginning, we can link environmental stresses and physiological responses. We can link that to alterations in brain physiology, or at least the brain environment in terms of hypoxia. It becomes more complicated, but it's still doable to link that physiology to alterations in cognitive function, or at least cognitive domains as described by the tests. But then predicting behavior from that is a difficult thing to do. So the model that I've arrived at when I get to do my PhD all over again, as I gather you get to do, the model I've arrived at is this idea of working backwards. So what we've done in our latter experiments is we've picked a simple key safety behavior, the act of throwing a reserve parachute. This feeds into a safety question that we've established from the literature is a problem. Why don't paraglider pilots throw their reserve parachutes when it might save their life? Often they don't. And we can start to ask, what part do environmental stresses play in this? So this is the sequence that leads up to a reserve parachute deployment. Somebody makes a poor decision. They behave in a way that is hazardous. Their wing departs normal flight, as you can see in the top left, part of it's collapsed. They then need to recognize the departure, not always as obvious as it may seem. They need to work to restore that wing to normal flight, but they need to recognize the fact that they're failing to do that before they hit the ground. And that's a cognitive shift that many pilots fail to make. And then they need to go through the act of deployment. So this is the sequence of behavior that we need to elucidate. So we started at the very end. We started out simply with that locating and deploying their parachute. So this gentleman here is on a zip line. He's in a paraglider harness. He's looking up at two LED lights, and he's trying to pull his paragliding brake lines in time with them. He's also trying to name everything he can beginning with the letter A. This together is an overwhelming thing to do. He's then released from the zip line and has to pull his reserve parachute as soon as possible. You indeed. So this approach has some advantages. The first is immediacy. So we were able to do this study in a large sample, in 55 people over the course of a day. So already we've overcome that small sample size problem. And we were able to see safety behaviors. So for example, 85% of paraglider pilots tried to locate the handle on the hip, not where it actually was. That enables us to feed back into design. We can say to harness manufacturers, you should put the handle on the hip. We found another behavior. Paraglider pilots tended to pull upwards instead of outwards, even though they were told that when they deployed their reserve, they should pull outwards. Sometimes the reserve parachute got stuck as a result. So these are immediate advantages. They don't necessarily help us with our overall question, but at least we get concrete results. More interestingly, though, things that now start to allude to what we're trying to achieve. What happens when they get equipment failure? We start to see repetition of the same action. We start to see freezing behavior. This person has pulled his parachute handle, but also part of his harness. All he needs to do is to let go of one of those black straps, but he can't do it for the duration of the zip line. He's frozen. We're starting to see underlying cognitive problems, domains that we might be able to map. Now let's apply a different environmental stressor. Instead of linear acceleration, let's try G-force. As this paraglider pilot doing the same task is spun up to 4G, she initially starts saying the words and doing the actions with her arm. At some point, she ceases to be able to talk and she locks her hands below the level of her harness. Actually, she locks her hands at a level where a paraglider could stall. Now, let's look at this in the real world. Let's go back to our complex task. We've now seen examples on the zip line of freezing behavior. This is someone trying to deploy their reserve parachute. Listen out for the instructor. He's going to shout secours in French. That means reserve, deploy. If we can launch him at all. Paraglider departs normal flight. And finally, he deploys. With meters to spare. And if the instructor hadn't been there shouting secours, would he have deployed at all? Did we just see freezing behavior, secondary to G-force, secondary to that rotation in life? So in my last slide, let's tie all this together. We're trying to map how physiology affects brain function, affects cognition, and affects behavior. An approach that I've arrived at is that actually to do that in a complex activity, you have to start with a very simple behavioral question. In a large sample, you have to identify exactly what those cognitive domains that are impaired are. You can then use a large sample again to find a threshold for when those stressors kick in. So in our G4 sample, we had 88 pilots over 2 days, much better than the 10 we managed in the chamber. Then you can go into a chamber, then you can go into a lab. You can start to simulate based on what you've seen in a complex environment, and you can start to do the kind of work that Joe and Tom do. You can start to describe the physiology of brain and body, and you can start to use cognitive tests in the domains that you've identified as being a problem. And then comes to my mind, the key bit, the bit that closes the loop. Having done all of that, from those physiological changes in brain and body, can you predict the behavior out in the field again? And if you can do that, then I think you've truly closed the loop. And then the next step is to repeat that loop for every part of that behavior. Deploying the parachute, recognizing the failure to deploy, attempting to restore, recognizing departure, winging departure in the normal flight, and the poor decision-making and control. And so I would argue that if you want to truly join all those dots, this is an approach to doing it, but that doesn't underestimate the labor or the complexity of what's involved. Thank you very much.
Matt, thank you very much indeed. That was a fascinating talk, and thank you as well to Joe for your talk too. So we'll now begin our Q&A. And a couple of questions about variability. And that to you, Joe, in the first instance. Your study described four trials, 4 different conditions. Did you randomize the order of those trials? I'm sorry if I missed you explaining that.
Yeah, so it is a really good question. And of course, you would increase the risk of an ordering effect if everything was to be done in the same order, with the severity being increased or decreased in the hypoxic stimulus. But they were randomized, yeah, between individuals.
Okay, great. And another question from myself, I have to say. If you simply, so you had 4 different conditions, but if you simply repeated one of the conditions, you know, would the influence on cognition be the same?
Yeah, that's a really good question. One we actually thought about quite a lot. My PhD student, Tom Williams, and myself and the wider team spoke about that at length before we started this study. Couple of things on that. One is the participants attended the lab on a number of occasions. So there was health screening, familiarizations. I think they did 7 or 8 familiarizations with all the tests until there was a very small coefficient of variation between their tests. So we tried to obliterate a learning effect on the tests. And then there was 4 experimental trials. We contemplated bringing them back for a 5th, almost as a second control. But we were very happy with our control condition, so the normoxic control. And the data was almost identical after the 60 minutes. So we thought it might actually add more variability into our results than actually help us. But it's a really good question when we considered, and my answer is no. Because the short duration, I think it would be quite consistent, and based on our pilot test, I'm pretty confident it did.
Okay, and just to sort of follow up, but on the same theme here, Joe, we have a question from Nina Cherocek. Sorry, Nina, I've pronounced your name so badly. Nina says, you mentioned a minimum 48-hour washout between your trials. Were these controlled for time of day? Because there's a large inter-individual time of day variation in cognitive function and blood biochemistry. And Nina wonders if that could explain some of the noise in your data.
Yeah, that's a brilliant question. And the answer is we did. So all these experiments were done at the same time of day within participant. And I think all bar 1, maybe 2, were done in the morning to try and offset that between individual and also within individual variability and all those biomarkers mentioned. So yeah, definitely. I think we're within 30 minutes of each trial in terms of the same time of day. So yeah, that's a really good question. We made sure we did that.
Okay, great. Okay, so looking at the Q&A, so we have another question here from an anonymous attendee. If cognitive function declines with TSI at altitude when at rest, what would happen to decision making during exercise at high altitude? Presumably there'd be more competition for the already limited PaO2. I could maybe direct this question to both of you, actually. What do you think would happen at exercise at high altitude if you're seeing these phenomena at rest? At normal altitudes, sea level.
Thank you. I mean, I think Mont Blanc is an example of that happening. I think that's what you see. I think you see competition for already limited O2, and I think you see a decline in function and some not very good decision making or behaviour. Interestingly, and I'll pass over to Joe at this I believe is the subject of his next experiment.
Good question then.
Yeah, thanks, Matt. I swear I didn't plant that. I'm definitely not anonymous. Couple of things on this. Yeah, we have a couple of studies underway looking at this at the moment. Of course, COVID has put a stop to these studies when we're halfway through. But what people need to, I suppose, consider as well, that exercise in itself is a stressor. And all the exercise physiologists in the panel or in the attendees will agree with this. There's a lot of literature out there looking at the effects of exercise in a normal environment, so not in a hypoxic environment, not in a hot environment, not in a cold environment. And there's significant research to suggest that if it's moderate intensity exercise, acute moderate intensity exercise, it can actually improve cognitive performance. But then as the severity of exercise or the duration of exercise increases, it'll actually lead to an impairment in cognitive performance. What we've done literally only a couple of months ago, my colleague in Japan, Professor Suichi Ando, and I actually reviewed the literature on the combined effects of exercise and hypoxia on cognitive function. And for every study that shows an improvement in cognitive function, there's an impairment, and then some more showed no change. And we could only come to the conclusion that it's an interaction of the severity or the intensity and the duration of the exercise, and also the duration and severity of the hypoxic exposure. And it's the knock-on physiological effects from that will actually decide what happens to cognitive performance. But it's a really interesting question, and it's not one that's easy to answer. I'd certainly direct you back to that review that we've published a couple of months ago in the Scandinavian Journal, Medicine and Science and Sport.
Okay, thank you, Joe. An interesting question here, again for both of you really. Have you ever considered, this is from Lijun Shang, have you ever considered any gender differences at all? Joe or Matt, have you ever any observations on whether there are any gender differences in any of the phenomena that you've been studying?
When you look through the available accident literature in paragliding, there's a preponderance towards higher accident rates in female pilots. So I am very interested in whether there is a gender difference there. It's something that we've not been able to look at in our simulator studies with any power because the sample sizes were too small. When we did that in our zipline studies, what we actually identified was gender bias in how the kit was made as much as anything else. We identified biomechanical problems in parachute deployment that meant any underlying physiological effects or gender effects there were masked by that. So we need to get the gear right, and then we can test it properly.
And then you can, yeah, right. Thank you for that. Another question now. From Carl Friedel. Sleep restriction produces similar high-level functional declines, best preserving critical brain function. Were the lab study subjects controlled for sleep? Yeah. Had they all had a good night's sleep before they came into the lab?
Yeah, Carol, that's a great question. And we recorded that. So we recorded the hours sleep the night before and looked at sleepiness, and a lot of that information was asked throughout the POMS questionnaire as well. So yes, everyone attended the lab with the same self-reported granted level of sleep. We didn't quantitatively assess it. But what I will say is we're actually in the middle of a study now where we're looking at sleep deprivation in combination with exercise and a hypoxic dose as well. TSI, or cerebral oxygenation after sleep deprivation, has a very, very similar decline to what you'd actually see from a hypoxic stimulus. And they're increased, they're additive when you combine sleep deprivation and hypoxia. So that's certainly an under-examined area of research, and one that we're looking at the moment.
Absolutely, and you know, if you translate that into the field, Matt, you know, it probably too early days and not enough research, but you know, in terms of recommendations for participants in these sports, perhaps they could be encouraged to sleep well before they compete.
Well, actually alludes to one other thing though, which is that there's a further challenge here, which is that when you do find these things, you can't just confine them to our community. You have to communicate these quite complex and nuanced ideas to your participants in a way that is meaningful, and that's not always easy. And you see that very clearly in mountaineering and high altitude trekking, where SATS probes have become a very common sight on treks up Kilimanjaro or to Nepal, but without an understanding of what they mean and their limitations of oxygen saturations in that environment. And that's led to decisions being made for people to either continue or go down, probably inappropriately.
Absolutely. Okay, thank you. Another question. Sorry, so we're sort of flicking from topic to topic, but I'm trying to address as many of the questions as we can. We're back to variability now. This is a really interesting question for well, two questions from Callum O'Malley. But I'm gonna go to Callum's second question. He says, sorry if I missed it, but were your participants blinded to the condition? If not, what would you expect, and this is to Joe, if you blinded the conditions and included a placebo trial where a participant may be informed they're hypoxic but are in fact at sea level?
Cracking question.
You tried that.
And I think you stole in one of my ideas because we've talked about this at length. It was amazing, actually. People in a normoxic condition believed that we did blind them, actually, to answer the first part of the question. But people, when they were normoxic, thought they were in the most severe hypoxic trial, and vice versa. Absolutely none of the participants got the ordering correct. So we actually queried whether running a study and a deliberate concealment or deception study, 2 trials, both normoxic, but somehow let it slip in one of the trials that, oh my God, this is the hypoxic one or something. And actually seeing if there would be a placebo effect and people would actually have impairments in their cognitive performance because they believed that they were feeling, I don't know, fatigued or tired or whatever, not as cognitively with it as they would be. But yeah, if you want to talk to me afterwards, it's definitely a really nice study to do in there. So we definitely should collaborate on that idea. I'd be very open to it as well.
Carolyn, can I just
Great.
add something to that? Just
Yeah,
to
sure.
follow up on Joe, we've done, and others have done, quite a lot of studies using sham treatments, using placebos, using false conditions. And pretty much consistently, you'll see whether or you put somebody into a competitive environment when they're not, it's a perceived competitive environment, or whether you put them into water that they think is 5 degrees colder than it is, it completely changes their responses. And so this area of the interaction between physiology and cognitive function in terms of the outcome and the kind of ways people behave and the decisions they make is an absolutely critical area. And it's one that I think we've neglected because of the difficulty in doing it, because we think as physiologists, it's not our part of ship. But it very much is, because as Matt has shown, when you get into the real world, and I see some of the questions like from Kate O'Brien, when you get into the real world, I mean, that's the big end point. Do you make the right decision or do you not? Do you keep going and trying to summit and end up having a problem, or staying in the cold, or continuing exercising in the heat, or do you not? So we really must start to close this loop.
Absolutely, absolutely. Now I've got a question. Where are we? I just want to explore before. I mean, we've only got a few minutes left, and I know that that I think, Mike, you wanted to tell us a little bit more about mechanisms and the ideas collectively you have about mechanisms. But I've just got a question here from Jeremy Walsh. Have you considered applying inter-individual variability statistical approaches as a means of identifying participants who are more susceptible to hypoxia, and seeing how their physiological responses match up with this decrement? So perhaps offering some insight, if you haven't already, Joe, into analytical approaches.
Yeah, I'm not sure if I'm going to answer the question specifically from an analytical perspective, but what we have done recently is we've looked at the variability in SpO2 signal. So like what has been done in terms of heart rate variability, we've turned that around into SpO2 variability. And we've actually published a couple of papers recently, one using a network physiology approach and the other purely just looking at SpO2 variability at the same graded levels of hypoxia, normobaric hypoxia. And it seems to give a very good insight into what is happening to an individual. And SpO2 variability, for example, at an individual level was correlated with breathing difficulty, whereas SpO2 in isolation wasn't correlated with breathing difficulty. So that's certainly another avenue that we're looking to explore moving forward, is the variability in the data for sure.
Mm-hmm. Okay, great. Thank you, and thank you for your question, Jeremy. We've got a couple of minutes left, and Mike, do you think you'd be able to take us through the paradigm? Because you know, one of the things that comes across here is that we still really haven't cracked that link between you know, the cognitive change and the decision making. So could we just have a look at that? Apologies to those whose questions we haven't been able to answer, but we're here on the chat, and Matt and Joe will be able to pick those up. So Mike.
Well, thanks very much. This is really something which we've put together, and Joe has been the lead on it. So I don't know if, Joe, you want to... It's a first stab at trying to put some mechanism into what otherwise has been largely descriptive in terms of what we find when we look at cognitive function. Joe, do you want to say a few comments about it?
Sure. I'll caveat it by saying we haven't published this. This hasn't been peer reviewed. We've alluded to it in our publications, but for the purpose of this, we decided to put this together. So if you start with a high altitude environment or a low FiO2, or interestingly, hyperthermic individuals, hypothermic individuals, and various other clinical conditions. And Mike talked to this at the start, one of the first things you'll see is changes at the brain level, whether, for example, if it's impaired uptake of mitochondrial oxygen, or a non-uniform reduction in O2 across the brain, particularly with the redistribution of oxygen to the regions of the brain responsible for more homeostatic purposes, cardiorespiratory control, etc. That is likely to lead to some sort of dysregulated brain network, and importantly, impaired neural connectivity across various brain regions. And this may actually be most prevalent in the complex central executive tasks, so the more challenging tasks where there's several planning things that go on. It's not purely reaction time, as Matt very nicely alluded to in a lot of his presentations, where people have to make quite big decisions. And if this impaired neural connectivity is probably most likely related to the cognitive impairment. And the question is this a positive feedback loop? Does this actually increase risk-taking behaviours? And ultimately, does it go all the way back to mean people continue to put themselves physiologically at more stress and potentially making the issue worse rather than improving it?
Okay. Mike, do you want to follow up on that?
No, just confirm that this is an unpublished, you know, very low in evidence first stab at trying to go a little bit away or more towards a mechanistic understanding of what's going on, and also start to think about whether some of these extreme environments, whether it be hot, cold, altitude, whether there is a common pathway that's impacting on things like cognitive function. And we've kind of settled and focused on decision making because it's such an important thing. You know, we don't have time now, but there are so many examples of people going under physiological stress in an extreme environment, making a bad decision, which then augments the stress they're placed under, which means, and they make another bad decision, and that this horrible descending spiral that they get into. So this may well be wrong, but at least we're starting on that road. And we encourage others to close that loop between the physiology and the cognitive function and decision making.
Great. Thanks, Mike. And once again, apologies that we weren't able to get to all of your questions, but thank you to all of you who submitted them. And I'll now hand back to Mike for some closing remarks.
What we will try to do, for those of you, I've seen questions from John Leach and others, we'll try and answer those questions hopefully offline. The guys, there's a couple of, I think your PhD examiners asked a question, Matt, which would be a very good idea for you to try and answer. Okay, folks, thank you very much for attending this. There's a couple of important messages I want to give before we finish. I want to encourage you to sign up to the Physiological Society Human, Environmental and Exercise Physiology theme, or any of the other themes that you are interested in. There's plenty of information on the Physiological Society website about that. The Society runs lots of meetings online, from webinars to longer meetings, and also courses. So more information is available on the Society events page. And I'm going to make a little plug, because we've had so many comments about variability, that Professor Igor Mekovic and I are jointly running a 2-day meeting with the Physiological Society on how you deal with variability within data on the 5th and 6th of October. We're going to be looking at research in extreme environments, as well as research in things like clinical settings. So the variability that we've seen in the outcome of various COVID situations in patients, as well as engineering variability. So the important point about that is there will be some absolutely first-class statisticians involved in that, who will be talking about how you deal with that variability and the extent to which actually you want it. So sign up for that if you're interested.